Now what about WI? Let's look at WI, which we have assigned. It's W intersection CI plus F, which is, we just did the maths, no? So it is like 2k plus 2 divided by 2 plus k plus 1, and we have shown that this is less than or equal to 2k plus 3. So it is indeed true that when we recursively call, right, like by induction hypothesis, what we know that if I'll give up, so what does this imply? By induction hypothesis, now we can apply induction. By induction hypothesis, okay, there exists, right, there exists a tree decomposition of GI, okay, graph GI that we created, of GI of width 3k plus 4, okay, of width 3k plus 4, and what is this? Say Ti, and let's say Xi and T invert x of Ti, okay, okay, and okay, so of width this, and what is the property of this, right, is that Wi is contained inside, let's say is contained inside, say, xri, this is a root xrii, okay, where ri is the root of Ti, okay. So this is given to us. So now how can we, so now what will I do to make a tree decomposition of G? What will I do? So here is my these are my T1, T2, Tm, okay, these are the trees and their assignments. Now what I'm going to just do is going to add, and now these all are rooted at R1, R2, Rm. So these are like rooted at their root, okay. I'm going to make, so for the tree structure for G, okay, I'm just going to make one root, call it R, and make him adjacent to. So this is my tree structure. And what I'm going to assign XR to be, I'm just going to assign XR to be equal to W union X. That's it. Now XR is equal to W union X, okay, which implies that the size of the bag XR is, what is W? W was like 2k plus 3. What was X? Sorry, this is not X. W union S, k plus 1, which is 3k plus 4. Okay. Now, why is this a valid tree decomposition? Let's ask ourselves, why is this a valid tree decomposition? Look at any edge of, look at any vertex. Definitely, definitely every vertex appears in some of the bags because, okay. And what about any edge? So where is my edge? My edge is either completely contained inside here, or it is completely contained inside here, here, or here. Now, all these edges are being taken care when we talk about Ci union S. So every edge is perfectly fine. But what about connectivity? So now, if a vertex only appears in C1, its connectivity is given by induction hypothesis because of the TIs. Okay. Now, vertex of W could appear at several places, right? W, because it could belong to S. So basically, what happens is that for those vertices in S, okay. Now, if those, like, so you could have a subtree, fix a vertex here. Okay. So the only vertices only vertex who could appear in several pieces is a vertex of S, right? So now look at a vertex of S, right? Now, so look at fix a vertex of S. Let's say we fix a vertex U in S. Now U could appear several places. So now look at its look at its connected pieces. Like maybe let's use slightly different color. Okay, so maybe it appears here in some connected pieces, appears here, maybe appears here. Okay, now notice this is a vertex of S. It means it is assigned, look, every vertex of S is part of Wi, and I know that Wi appears in the root, which implies that actually this tree must look like this, this must look like this. And now what is the property? The vertex of U is also part of this, so I know that there is also a node like this. It means this gets connected, right? So that shows the connectivity part of this, which means that indeed what we have obtained is a valid tree decomposition of width 3k plus 4. Okay? Okay. Yeah. So we have shown to you that, so what we have shown now, that indeed if a graph has this weighted balance separator with respect to 0, 1 weight function for every weight function, then its tree width is indeed upper bounded by 3k plus 4. Okay. But in this proof, proof is not algorithmic. And the question is why? Okay. So the only reason this proof is not algorithmic is that when we apply induction hypothesis, we can make a design, we can replace induction with recursion. But what is not clear to us that what we used is right. So the computation of S, we said, well, when we were trying to do, you are given W, we assigned a function which assigned every vertex of W1 and 0 and say, hey, because this graph belongs to this, it has such a balance separator by definition, and you apply that algorithm. So basically it's a part. What is missing is that, okay, so the part which is missing is the following. So you are given a graph G, okay, and a weight function, 0, 1 weight function from say F, from vertex set of Z to 0, 1, and what do we want? Output a set S of size k plus 1 with the property that every connected component C of G minus S has weight vertex set of Z divided by 2. So can we do this? If we can do this, then we can make our algorithm constructive. Okay. So next, our idea is to make this separation algorithm and then induct that separation algorithm into the piece. Okay. 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 So there are. Okay. Okay. So now क्लास पढ़ा रहा हूं पापा, अभी मत डिस्टर्ब करो. Okay. So set S of size k plus 1 with the property that every component of C of G minus has heavy. Now, first of all we know that suppose you have a set S such that weight of every component is weight of at most this, then can I compute this set S effectively? Okay. So suppose this is my piece, this is my piece, this is my piece, this is my piece. And maybe let's write down the W. Okay. Now let's look at this W. So let's call this W intersection Ci as, let's call them, let's say some Si or Zi. Okay. And let Ni equal to cardinality of Z. Okay. And let's call Ns equal to W intersection S. Okay. Now what is the property of this? N1 dot 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 Nm plus Ns equal to cardinality of W, which is like whatever. So we will be given some 2k plus whatever the size may be for now. Okay. Okay. So, but notice we do see W. Okay. Now I want to ensure that W gets in the proof. What we use is that the only time we use that, well, look at the W intersection Ci. Okay. Cardinality of this is upper bounded by cardinality of W by 2. How can I ensure that this happens? Okay. So to ensure that, what we will do, we'll say, look, let's guess how W is distributed. Okay. So let's guess how W is distributed here. Okay. And so what I will say that, look at W, we can partition W into A, some piece, disjoint union W intersection S and B. Can I group W into these pieces, okay, such that A and B are large enough but not too large? Okay, we'll quantify what this means. Understanding W intersection S is easy. Guess, right, and delete them as they are part of S. Okay, okay. Okay, guess and delete them as they are part of S. That's great. But what about, how do I guess W1 and W2? Now, that's also easy actually in some sense, because right, because still it's a function of k, so I can guess some A and B, which is basically will be collection of some green spots, and B being some collection of green spot, such that, I mean, you need to delete some vertices of S, this property happens. But notice that I want that W are separated nicely. It's not that one piece contains large fraction of W in the sense that, oh, it contains all but say 2k minus 10 and 10 vertices here. We do not want that to happen. So to do that, I need to show to you, imagine yourself that the property of A is that, and B is that they are at most 2k by 3. Suppose I am able to prove that cardinality of A and cardinality of B is at most 2k over 3. Then what happens that I guess this partition A and B of W. I guess this partition of A and B of W. One second. Okay. I guess this partition A and B of W. Okay. And then I will say, okay, find me the minimum balance separator which separates A and B. Okay. Let's delete this vertices. Now, what is the property that when I delete this, there is no component that contain both vertices in A and vertices in B. then what happens if you look at any connected component after you have deleted this, right? It can only contain either a vertex of A, either a vertex of B, but it cannot contain both vertex of A and B because we have separated A from B of the minimum size. Then what happens? Then any connected component can have vertices at most either A or at most B, which is at most 2k over 3. And then I will show to you how we can make use of this also to make progress. Okay? So that is the whole idea of our algorithm, is that I want to say to you that look, there exists a partition of my W into A and B such that no A and B are large, and then I want to find a balanced separator of that piece, right? And yeah, and then I want to find the balanced separator of this A and B such that this property holds. Okay? Okay. 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 So we know that the property that with respect to this weight function f, right? Okay. So basically, I shouldn't write. So the what is I should write. This is not right way to say. Suppose G belongs to Z weighted 0 1. So like it has a property with this that of k plus 1. Okay. Then what happens? Okay. Okay. So you know such an object exists because G belongs to this. Okay. Look, we don't know whether G belongs to this or not, but we will be able to check. Suppose if it doesn't belong to this, we will be able to show that something bad happens. Okay. Okay. So now what will we do as an algorithm? So first let's try to show something interesting here. Okay. Okay. So here is my set F, okay, and here are my components. Okay. And what is the property of these components? Like and this is my W gets distributed here, W gets distributed. So suppose this is like what is the property of each of these NIs? The property is that each NI is at most, let's say, cardinality of W is say Q. Okay, say it's Q over 2. Then I am telling you that there exists a partition. Okay, then I am going to show to you there exists a partition A and B with the desired property. We have seen this before, but let's repeat it once again. Okay. Without loss of generality, assume that N1 is larger than N2 is larger than dot 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 in M. Okay. I first check myself. Is N1 greater than or equal to Q over 3? If it is, then we are very happy, because then I am going to take A as, then what I am going to take A, look, and I am going to I am going to take A as W1. So suppose Z1, and remember that this is like this set was called Z1, Z2 and Zm, and this set we called it Zs. Okay. So what will I take A as Z1 and my B as Z2 disjoint union Zm. Okay. So this is how we will partition. Now let's assume that N1 is less than or equal to Q by 3. Then let L be the least integer such that L1 with L be the least integer such that if I do summation Nj equal to 1 to L Nj, it is becomes greater than q over 3. Okay? This is the first time it becomes greater than q over 3. So then let's ask ourselves, first of all, since n1 is less than q over 3, what do we know? All n2, which is less than n3 dot 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 nm, everyone is, sorry, right? So every number is at most q over 3. So what is summation j equal to 1 to L and j is less than equal to summation j equal to 1 to L minus 1 nj plus nj, which is less than equal to, because this is at most q by 3, and what is nj is another at most q by 3, because which implies that this is at most 2q by 3. Okay, great. Right? It is at most 2q by 3. Okay? But we also know that this quantity is strictly greater than q over 3 by our choice of L. Okay? Which implies that what is my A then? My A is going to be Z1, Z2 dot 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 ZL, and my B is going to be ZL plus 1 dot 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 Zm. Which implies that if you sum this number, what is the, okay, so I know that if I cardinality of Zi, I going from 1 to L is at least q over 3, at most 2q over 3. Okay. Now summation I going from L plus 1 to m Zi, what is this? This quantity is at least q over 3. So this is at most 2k over 3, and since it is at most 2q over 3, this is at least q over 3. So in fact, there does exist, if we have a separator S with the property that it can, like such that if I delete it, every piece contains at most half the vertices of W, then actually there exists a partition of vertices that is not contained inside S into two parts. Each part has size at most q over at most 2q over 3. So now what will I do to find? So now you gave me W. I will partition this into A disjoint union S, like A belongs to S and belongs to B. How many such partitions are there? Okay, so this is basically partition of W into 3 pieces. So this is upper bounded by 3 times cardinality of W, right? 3 times cardinality of W. Okay, so it like, right? So once we have done this, so what will this tells us? That it tells us that look, you wanted me my W, if what will this tells us? That look, I do this, okay? Suppose there exists a set S with the property that this holds, then I will do what? Here's my algorithm. Delete G minus S, delete, let's call this capital Y, delete Y, okay, delete Y, find a minimum sized separator from A and B. Okay. Okay. So now what we know, if minimum size separator, let's call it Q, if cardinality of Q is more than k plus 1, this part is invalid. Okay? Okay. Okay. Now, okay. So, because you know that there, why? Because you are guaranteed that if you delete for at least some if for some choice of s minus y, like if you delete s minus y, you know that a and b get separated. You know, they're guaranteed. So, and its size is upper bounded by k plus 1. So, if the kernelity of q is more than, in fact, you shouldn't say kernelity of k plus 1. If kernelity of is k plus 1 minus y, then you should say no. Okay? Okay? Or then maybe you found this, but now, if you found this, then what is the property? If you found this, then you are done, because then what is the property of q union y? The property of q union y is that if you delete q union y, look at any connected component. Okay? Any connected component has the property that either it contains a vertices from A or B. So, if I look at the intersection of W now to this component, okay, this, so W intersection Ci is upper bounded by either A, or W intersection Ci is upper bounded by B, which is upper bounded by whatever, 2 times W divided by 3, which is at most 2 times W divided by 3. Okay. So, there is a balance separator. Okay. But what happens, so this happens. Now, what happens that for every A and B, if every part you fail this, it just implies that this part is like for every partition of A, like A, Y, B, if you fail, it just means that the graph G does not have a desired S, and then you say, hey, tree width of G is definitely larger than this. So, this is the time when you will return no. Okay. If fail for all partition of W into A, Y, B, then return that tree width of G is strictly greater than K. Okay? Because if the tree width of G was at most K, then we will definitely find such a Jigsaw partition for which we will find the desired S with the properties. Okay? Now, notice that in our existential algorithm, we needed half to do all this. Okay? But since we do not have half anymore, okay, we will do something more. Okay. So, now okay, so for the algorithm, okay, so for the algorithm, what we are going to do, okay, inductively we are going to have W, you will see W. So, remember, so at any point of time in our algorithm, we were constructing, we had a graph G and a W, and of course, okay. So, now the cardinality of W that we are going to fix, okay, is okay, let's see. Okay, let's see how much we are able to fix this time. So, where did we use the fact? So, if you recall correctly, right? So, what we did, so we given this W, we found a separator S, okay, and we had these connected components C1, C2, Cm, okay, and we actually say that, okay, this is the part where you recursively go compute. Now, we wanted to show that, look at this, say, look at this Vi, okay, which was nothing but Ci union S. So we needed to, and what did we set? Our Wi, the set Wi was basically W intersection Ci union S. And now both needed to have the sum property. Now, what was Vi? So to upper bound Vi, what we said? Okay, so we said, okay, let's, I wanted to upper bound Vi. So let's say, okay, let's try to upper bound W intersection Vi. And we said that, look at this W intersection Vi, it is cardinality of, it is what? It is W intersection Ci plus mod S. Now, what can I say now about W intersection Ci? Only thing we can say about W intersection Ci is this is at most 2/3 times W. We cannot say half anymore, plus mod S. Okay? And I want this to be strictly less than cardinality of W, right? Because then I will say that there is a vertex of W which is not in this part, and hence the size of this graph is upper bounded by something. So now, if I do this, so what do I get? What I get from here is that 1/3 of W, right, should be greater than cardinality of S, right? 1/3 of W should be, because I just taken should be greater than equal to S, which implies that W should be greater than equal to 3 times mod S. Okay. Now, what is the meaning of this? I know that the mod S has size k plus 1. So, W better be 3 times k plus 1, which is 3k plus 3. So, now I am going to set W is equal to 3k plus 4. Okay, that is it. So, I am going to run my algorithm. Okay, I am going to run my algorithm. Okay, so what is my algorithm? My algorithm is as before. Let's go back to our algorithm. Okay, okay, okay. So, this is going to be inductive algorithm, but now let's copy. Paste. This we did already. Copy, 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 copy. Okay. Okay. So now I'm going to, this is the same thing. Wait here. This, then this is true. But now I'm going to give you an algorithm that computes one with 4k plus 4. Okay. So now rather than having this 2k plus 3, I am going to replace this with, what did we get just now? 3k plus 4. Okay. I am going to replace this with 3k plus 4, and we are going to, so 3k plus 4 plus k plus 1, and so that will imply 4k plus 5, which is nothing but 4 times okay. Yeah, so we'll give a tree decomposition with this, okay, 4k plus 5 width. Okay. And again the property of width, but now the width has increased to 4k plus 5, so the W is XR for everything. So now how we'll do? Okay. I think there is something missing. There is something missing here. Okay, sorry. I think there is some page missing here. Okay. So again my step will be that, okay, if the number of vertices is less than say 4k plus, if the number of this is going to be 4k plus 4, okay. So so if the number of vertices is going to be at, so now we are going to replace this item, okay, with, if n is less than equal to 4k plus 5, then one node tree decomposition. Otherwise you assume that the number of vertices in the graph is more than say 4k plus 5, and be such that again you will do the same thing, but now then you append it so that it becomes equal to 3k plus 4. Just for simplicity, you again do this 3k plus 4, you assign this weight function a separator S, right, and this is where we will make all the changes, right. We needed to find this separator, okay. So at this place what will we do? Okay, this is the place we will say, okay, partition W into A, Y, B, okay, and in G minus Y, okay, in G minus Y find min separator, minimum separator, min A comma B separator. And by the way, you can find a k size separator in times k times the whole graph. So this is polytime, this is basically ST separator. So this can be actually done, okay. You find min AB separator, I will not worry about it, suppose this you can do in polytime, okay. Now if, and that was we called Q, if the Q has size more than k plus 1 minus mod y, say invalid partition, okay. If succeed, take S equal to Q union Y. If all partition fail, return tree width of G is more than K, okay. So this is what we did. So now we needed this balance separator, so we will apply these algorithm and get this S, okay. And what is the property of this? That I cannot say the weight of C is this, but now I can only say that this is 2 times 3, okay. We cannot say because of that, right, we are only guaranteed that this is what it is. Okay, and again we need to have invariant all this, and that will happen. So if you just do the maths again with not half but 2/3, you will succeed and prove everything, right? So then by induction hypothesis you will get a tree decomposition, like by on the smaller graph. This is a recursive algorithm, right? So by the smaller graph you will get a tree decomposition. You can combine the tree decomposition everything, but now it will, because you are getting something like this, you will get a tree decomposition of the desired size. Okay, so this is what the whole algorithm will be. So I have written down this whole algorithm. Okay, so it's taken, it's a picture from a book. Okay, but basically this is what the algorithm does. Okay, okay, if the W is less than equal to 3, I mean, basically this is exactly what this algorithm does, is that like it actually it is, you can prove we don't need some 3k plus 4, but with 3k plus 1 itself things would hold, and like you make it equal, you find this what called weakly balanced separator or W prime with 2/3, let S be the such separator and this, and you can achieve this. So what is the running time of this algorithm? Okay, it is not precisely what we have learned, but this should give you how these kind of routines are written. These numbers could change here and there. So what is the running time of this algorithm? If the n is like at most some 4k plus 3, we just return one size tree decomposition, one node tree decomposition. Otherwise, you know, like otherwise we look at this graph induced on this union this. So it is like summation of the running time to compute the tree decomposition of each of the GIs. So this is what is written here, and now there was one running time to compute the particular W, which is like 3 to the power 3k, because it's like 3 to the power W and running time to compute the min balance separator. Okay, but notice that whenever we had this, we actually took this. So the size of the graph is basically Ni is nothing but, if I delete this, this is like N1, so it's like N1 plus k, N2 plus k, so on and so forth. Okay, so where these N1 to Mi are at most n minus 1, and what is the property that if I delete n minus I k plus 1, then this is equal to n minus k plus 1, because you have found a k plus 1 size separator and so on. So you can simplify this recurrences using this, and by induction you can actually prove that this is like T of n is like 3 to the power 3, big O of 3 to the power 3k n square. So an existential algorithm, all we needed to do in the existential algorithm to find a separator at some point of time. We don't know how to find that balance separator, so we reduce that question of finding balance separator to like finding an ST separator, still guaranteeing that the large fraction of W were not present. So every one not contain, we were not able to guarantee that they contain half of the fraction of W, but we were saying okay, but it doesn't contain everything, it only contains 2/3 fraction. So because of that, we were able to guarantee a constant factor approximation, but slightly more like maybe like, so existential algorithm says factor 3 approximation, this told us factor 4 approximation. Okay, I hope the algorithm was clear. You can do a running time analysis. This template was just given so that you know how these things are, but I took the liberty of like integers +1 +2 to make the lecture simpler and easier, but I will still keep this page to just to help you how these things are, how in general these things are, how formally you can write the running time, and how you can formally prove the running time using induction hypothesis.